Hello, everyone, and welcome to day 38 of Jamb Physics in 40 days. The series is gradually winding off. This is day 38. After now, we have 2 more days to go to the end of the series. So I want to believe that those of you that have been following the series so far, you've been able to gain a lot. By now, the confidence level should be really high because we've really covered a lot of topics. I want to say big thank you for always tuning in every day to go through with the series and for always liking and sharing the videos. And if you're yet to be subscribed to the channel, come on, just take a second to hit the subscribe button. And remember that is how you help us to continually make helpful content like this. So please click the subscribe button, and you can also hit the notification bell icon so that you get alerted every time we post new content. Now, if you're seeing this video for the first time, this is Jamb Physics in 40 Days, a series that is brought to you by Oya Learn, where we believe that when you are able to dedicate within 30 to 45 minutes of your time daily, you should be able to gather all the necessary tools that will help you ace Jamb Physics. So if you are a candidate who's preparing for the next Jamb and physics is one of the subjects you've selected, then believe me, this series is specifically made for you. So you want to check out all the videos in the series. You do not want to miss any of them. So please check it out from day one to the end. In each of the videos, we're being able to look at the individual topics that are in the Jamb Physics curriculum, and then we do a breakdown of what is expected of every candidate on those topics, that is the subtopics you should cover, and then we give you some hints and tips on things that you should remember before taking the exams. Then we go on to solve past questions on the topics while also giving you tips that help you solve those type of questions with great accuracy. So you see, when you're able to look through the series, go through the series from start to finish, you should be well on your way to score 90 plus in Jamb Physics. This is why you don't want to miss any of the videos in the series. So please subscribe to the channel and also hit the notification bell icon so that you get alerted once we put in a new video. And please, would also like you to put in more practice with the Exam Fun app. It's an app that is created with the intent of infusing fun into your study time. So if you don't want your study time to be a drag, the sure way to ensure that you infuse fun into your study time is to use the Exam Fun app. Now, to download this app, all you have to do is click the link in the description box of this video, and that will lead you to either the Google Play Store or the Apple Store, where you can download the Exam Fun app. So download it today and register and get in some practice. And the interesting thing about the app is that it's not just a fun app, it is also a rewarding app, in the sense that the more questions you solve, you can also earn some money. So download the app today, and we'd like a review also from you. So if you have any question concerning the app or concerning what we are doing on the channel here, you can always put it in the comment section. And if you come across something during your study time that you would like some help with too, we are interested in that as well. So please keep your comments coming, drop them in the comment section, and we promise to attend to every one of your comments. Now, what we're going to be doing in this video is elementary modern physics. Now, it's quite a broad topic, but we'll look at what is expected of Jamb, and then we'll be giving you some hints on things that you should always remember before you take the exams as regards this topic. Now, under elementary modern physics, what Jamb expects you to cover are as follows. They expect that you should cover model of the atom and their limitations, talking about models such as the Dalton's model, the Rutherford's model, the Thomson's model, and even up to Bohr's model, and the quantum mechanical model. So it's important that you're able to look through all these atomic models, how they were able to move from one to the other. You know that each of them is actually an advancement on the work of another person. When they see the limitation of what the first model says, then they advance on it and create a new model that explains what atoms should be like, even in a more better way. And the thing is that each of them has their limitation, which is what always leads to the next. So it's important that you don't just look at the models, but you also examine their limitations as well. Now, you should also be able to explain the elementary structure of an atom. That is, what does an atom actually contain? You know, it has a nucleus and then it has electrons revolving. And in the nucleus, we have the proton and the neutron. So you should be able to explain them, their charges, and how they behave in the atom. Now, you should also be able to explain energy levels and spectra. Of course, when you add energy to any atom, they get excited and then they move from one spectral point to the other. You should be able to tell what happens as they move from one spectra to the other and solve equations on this topic as well, which then leads you to understanding thermionic emission and the photoelectric emission. Jamb expect that you are also able to cover this topic as well as use the Einstein's equation for stopping potential. And that's when we talk about equations such as E equals hf, which of course is also hc over lambda. Remember that E is the energy change. It's often from one spectral level to the other, or it's just the entire energy in itself, that is the potential energy there. And then H is known as the Planck's constant, while F is the frequency. Now C here is the speed of light, while lambda is the wavelength of the emission that you experience or that you observe in that case. So you should be able to use this equation to solve many questions on this, including applying work function also to this. So though it's not added here, but when we solve questions on that, I would of course introduce you to the work function equation as we work with this particular Einstein's equation. Now, Jamb also expect that I should be able to mention the applications of thermionic emission and the photoelectric effect. You should be able to list them, and also you should be able to explain the simple methods that can be used to produce X-ray from vacuum tubes. You should be able to explain that, and also mention the properties of alpha, beta, and gamma rays. That is, how do they deflect in the field, and you should also be able to give their properties and also write equations that can be used to detect alpha particles, gamma particles, and of course the beta particles when you do fusion and fission reactions. You're also expected to be able to calculate the half-life of a particular material and then also be able to apply the decay constant equation. I have given the equation for the decay constant here. You should be able to apply this equation to find decay constant. And then you should also be able to explain the production of energy by either fusion or fission, and then explain binding energy, mass defect, and apply the Einstein's energy equation. It's often written as E equals mc squared, but you should know that there could be changes in the energy level. So at that point, we do delta E equals delta mc squared, where m is mass, c is the speed of light, and E is the energy either absorbed or emitted, or as it's usually said, radiated in this case. Now, you should also be able to explain the wave-particle paradox, that is the wave-particle duality of light. You should be able to explain that. It's also from the Einstein's equations. And then you should also be able to explain electron diffraction, and then finally be able to state the Anderson-Heisenberg's uncertainty principle. Now, these are the subtopics that are under this. As I mentioned, it's quite a broad topic. But what we are doing in this video is to prep you for Jamb. So instead, what we'll be doing is solving past questions that touch on all of these subtopics. So we should be able to solve at least one question on each of them as we go. And please, if you want a full understanding of this, I advise that you should also check out our video on the same channel where we talk on the modern physics itself. So each of these has been broken into different subtopics there. So you should be able to find each of them, whether you are looking for the wave-particle paradox, whether you are looking for the Einstein's equation for stopping potential. All of them have their videos also on the channel, so please check them out, because in those videos we explain them in more detail and then we solve multiple examples. So even if we don't get to cover everything in this video, you can find more from that video. And please don't forget to also share this so that many others can also have access to the video. So if you're ready, let's just go on to solve some past questions from Jamb on this topic. And don't forget, I'll be giving you some tips that will help you solve those questions with great accuracy. So if you're ready, let's go. If the frequency of an emitted X-ray is 1.6 times 10 raised to the power 16 Hertz, the accelerating potential is, the accelerating potential here is denoted V. So in order to solve this, there are two equations we have to put together. First, this equals, and then if we call this equation 1, And we know that E is also HF, right? So this is equation 2. So now we can equate both of them and say EV equals HF. Now accelerating potential is this V here. So to solve that, we make it the subject and then it becomes HF over E. So let's apply this. Now, Planck's constant is H, so that's 6.63 times 10 raised to the power minus 34. Okay? Now, the frequency is given here as, so we are multiplying that, so 1.6 times 10 raised to the power 16. Now, all of this is going to be divided by E, which is 1.6 times 10 raised to the power minus 19. So easily we see 1.6 cancels out. So V here equals 6.63 times 10 raised to the power. Now this is minus 34. So plus 16. Now when this goes up, it becomes positive. So plus 19. Now what does this mean? It means we have 6.63 times 10 to the power of. Now this is minus 34 plus 16 plus 19. Now plus 16 plus 19 will give us 35. So that's basically 35 minus 34, and that gives us 1. So power of 1. So when you multiply this, you get 66.3 volts. So from here now, we see our answer is already 66.3, and the option that has that is option C. So the correct option is therefore C. A certain radioactive source emits radiations that was found to be deflected by both magnetic and electric field. Now the radiation is, now for any radiation to be deflected by the magnetic or electric field, such radiation has to have a charge. So because the charge that determines whether it is going to be attracted by the positive plate of the electric field or the negative plate of the electric field, and vis-a-vis when we are talking about the north or south pole of a magnetic field. So it's important to recognize the charge that that material also has so that you can know the direction it is deflected to, because this same question can be twisted in that direction where you are asked about where it is deflected to. Now, one thing that is important to say here is that electromagnetic radiations themselves cannot be deflected by the electric field or magnetic field, and this is because they do not have a charge. So they are going to be neutral to it, so they will continue in their straight line motion that they were going before. So that is why rays such as the gamma ray, the X-ray and ultraviolet rays that are electromagnetic radiations themselves will not be deflected in a magnetic field, nor will they be deflected in an electric field. So the only thing here that will be deflected is the beta ray. Now this is because it is negatively charged, and as such is going to be attracted by the positive plate of the electric field, for example. And if it were alpha particle, that one is positively charged, so it will be attracted to the negative plate instead. So this is the only charged ray that we have here. So it is the one that has to be deflected by both the magnetic and electric field. So the answer is A. This question says, if the fraction of the atoms of a radioactive material left after 120 years is 1/64, what is the half-life of the material? Now, what's important that we have to do to this question first is to find the amount of time it takes for half of this material to decay. So in order to do that, we have to see how many times you have to keep removing half until you get to 1/64. Now, you could do this in two ways. Now, the easier way is this method here. So to find the amount of years in one lifetime, we're going to say 1/64 equals 1/2 in bracket of what? So what power does this have to carry to get to this level? So let's say this is unknown. So this will be 2 raised to power what? That is, to break this down, remember that this has to be power of something. So let's say it's power of n. Now, to solve this, we need to find the value of n. So we have to break this down until we get 1/2 as well. So apply your knowledge of mathematics to solve this using exponential equation. So this can be written as 1/, now this is 2 to the power of what gives us 64. Now 2 times 2 is 4, times 2, we get 8, times 2, we get 16, times 2, we get 32, then times 2, we get 64. So that is power of 6. I've counted 6 there. So, and this equals 1 over 2 to the power of n. Now, this can also be written as 1 to the power of 6. So I can say 1 over 2 in bracket 6 equals 1 over 2 n. So what this implies is that n equals 6. So it means it has gone through 6 lifetimes for it to get to 1 over 64. So now let's find the value of the years that it takes for it to get to, for each cycle to go. If n is 6 and has gone through 6 lifetimes here, so the amount of years in one lifetime is what we need to find. So that is, we'll then say half-life equals the number of years it has taken to get to 1 over 64 here, which is 120 years, divided by the number of lifetimes it has gone through, and that lifetime is 6, so divide this by 6. Now 6 goes in 12 2 times, and in 0 0 times, so we have 20 years. That tells us that the half-life is 20 years. So the correct option is B. This question is also on half-life, and it says a substance has a half-life of 3 minutes, and after 6 minutes the count rate was observed to be 400. Now we are asked, what is its count rate at 0 time? That is, before decay even started. Now, what we have to do here is, we say let the count rate be let's say x, for example. So it has x count. So after 6 minutes, what will remain? So remember, after 3 minutes, it becomes x over 2. And then after 6 minutes, it becomes x over 4. And it is this x over 4 that equals 400 counts. Okay? So to get the value of x, we just solve it mathematically by saying x equals 4 times 400. And this would give us 1,600. So it is 1,600 counts, which is option A. The mass of a proton is approximately equal to that of a. Now, instead of just going straight to answer the question, I'll give you the approximate mass of each of these, and then we can then pick our answer from that. So no matter how the question is flipped, you should be able to also give an answer to it. So let's have first a proton. Remember, approximate mass, okay? So we have proton, alpha particle. Then let's put down beta particle. Then neutron. Then electron. And just for good measure, let's just put in gamma too. Okay, so that's 1, 2, 3, 4, 5, 6. So we are actually killing 6 birds with 1 stone. So the approximate mass for a proton is 1.67 times 10 to the power of negative 27. And this is in kilograms. Okay? Now, the approximate mass of a neutron is similar to that of a proton. So we'll go straight to neutron, because to answer this question, the answer is neutron. Now, proton and neutron have close mass, but neutron is 1.675, right? But it's very close, so that is why the question says they are approximately equal. So remember, it's times 10 to the power of negative 27 as well in kilograms. Because if we are to approximate this 1.7, this is also 1.7 approximately. So they are very close. Now, next one to it is the alpha particle. The alpha particle is about 6.64 times 10 to the power of negative 27 kilograms. And then beta particle and electron have the same mass, and they are 9.11 times 10 to the power of negative 31 kilogram. The same thing for electron. Then gamma particle, it has no rest mass. So now that we know the mass of each of these, please keep note that the question could be twisted and they can say the mass of a beta particle is approximately equal to that would be for electron, because electron and beta particle have the same charge and also the same mass. Now for neutron and proton, they have the same mass. Well, approximately the same mass. Let's not say the same mass because they are slightly different. Okay, so but they are approximately the same. And I've also given you the mass of the alpha particle, and now we also know that gamma particle has no rest mass. But to answer this question, we'll put down option C. If you're yet to be subscribed to the channel, please kindly take a moment of your time to click on the subscription button. It's only going to take a second. Please click the subscription button, and you can also click the notification bell icon so that you get alerted every time we put out a new content. And I would like to remind you that your practice time can only get better when you work with the Exam Fun app. It's an exciting app that infuses fun into your learning time, where you get to answer questions on any subject of your choice across different levels, and then you score points and even earn some money. So it's both exciting and also rewarding. So you want to try it out, please click the link in the description box of this video to download the Exam Fun app today. And don't forget that if you also have any questions at all, you can always drop it in the comment section. We promise to respond to all of your questions and even give you a video response where necessary. So please keep your questions coming, and don't forget to like and share the videos so that we can reach a wide range of audience that are in need of content like this. Now, this question here says, natural radioactivity consists of emission of. Now, radioactivity itself is defined as a spontaneous emission of radiations from atomic nuclei. Now, the radiations that are emitted from that natural radioactivity, it comes with alpha particles, beta particles, or gamma rays. Now, it is not always the three of them. There are sometimes you just have only alpha particles. There are sometimes you have alpha and beta particles, or alpha and gamma particles, or beta and gamma particles. And there are some times where you could have all three of them. Okay, so it could be either one of them, or two out of the three, or the entire three of them. Okay, so for natural radioactivity, what you have is alpha, beta, and gamma rays. So the answer is therefore C. Which of the following statements on the use of X-rays is incorrect? Now, X-rays are used. Now, A says in hospitals to obtain photographs of tissues and bones in the body. Now, we know this is true because whenever doctors need to know if a certain patient has a fracture or if there's a tear in a particular tissue in the body, what they do is they take an X-ray of that region of the body. But they also have to take precautions because it's an ionizing radiation. So this is correct. It's true about X-ray. Now B says for treatment of malignant growths like cancer cells. Now there's a particular kind of treatment plan for cancer that is known as radiotherapy. Now that is when the person is exposed to radiations that then kills the cancer cell or stop them from growing just enough for other treatment measures to kick in. Okay, so in this kind of therapy, X-ray is one of the radiations that can be used, as well as the gamma ray as well. So mostly they also use X-ray. So that means this statement is also correct. That is, it is true for the use of X-rays. Now, option C says in detecting fingerprints. Now, whenever there's a forensic work that needs to be done and they have to detect the fingerprints in a particular region, they do not use X-ray for this. Now, what they do is the use of powder and UV light. So with the UV light, you can be able to find hidden fingerprints in any location, whether you are using for an investigation, in forensics, and the likes. So we don't use X-ray for this. UV is used for it instead. So this is incorrect. Now, option D says to reveal hidden flaws in metal casting and welding joints, which is true. Like for example, if you're trying to see if there is a leak in a pipeline, one of the ways they can do that is to use X-rays. And then option E says to detect alterations which have been made to works of art. Basically, in museums, they use X-rays to know if the work of art that are in display there are still what they are, if they are the original. If they have been replaced with a fake one, they can easily tell when they expose them to X-rays, because it will show the kind of alterations that have been done to that work of art, so they can use it for that purpose as well. So A, B, D, and E are true. They are correct. So C is the only incorrect one, so we go with that. This question says, which of the following statements about radioactivity is true? So let's look at the statement and then we declare if they are true or false. Now, statement 1. Alpha particles are positively charged. Now, you know that alpha particles are similar to what we know as the helium atom, and they have a +2 charge, so therefore it is positively charged. So this is true. Beta particle is negatively charged. Now the beta particle is similar to the electron, and the electron is negatively charged, so which means beta particle is also negatively charged. So this is true as well. Now statement 3. Gamma ray is neutral. Now we know it's an electromagnetic radiation and it is not deflected by either the magnetic or electric field, so which means it does not have any charge, so it is therefore neutral. That means this is also true. Now, statement 4. Beta particles has the same mass as helium. Now, this is false because the particle that has the same mass as helium is the alpha particle. So, this is false. And then finally, V says gamma ray is charged. We've already established that gamma ray is neutral, so it cannot be charged. So, therefore, this is also false. So we only have 3 true statements, which is 1, 2, and 3. Now the option that says 1, 2, and 3 only is option B. So the answer is therefore B. The mass of a nucleus is now when we say the nucleus of an atom, remember that an atom consists of the nucleus and the electron. Now the nucleus is actually a combination of proton and neutron. So to get the mass of the nucleus, you need the total number of protons and total number of neutrons. So the correct answer here is option A, total number of its proton and neutron. Which of the following is or are the limitations to Rutherford's atomic model? Now, the Rutherford's atomic model is one that describes atoms to have a dense core. That is, most of the mass of an atom is situated at the center of the atom, which is actually positively charged. And we know that center to be called the nucleus. Remember, the nucleus contains neutrons and protons, right? And then it says that they are negatively charged electrons that are revolving around that center core, or the core of the atom. So those electrons continue to revolve around it. That's how Rutherford describes an atom. Now, this description has some flaws, and this question is asking us to pick out which of the following are the flaws to that model. So let's look at it. Now, the first statement here says that it is applicable when energy is radiated as electrons are revolving. Now, this is actually from one of the limitations to Rutherford's model, in the sense that when you consider Rutherford's model, it's only looking at when an atom continuously emits energy. Because whenever you see that the electrons are constantly rotating around the atom, it means that energy is being emitted. Now, it gets to a point where it loses all its energy and is supposed to spiral into the nucleus. But this is not seen when we conduct the experiments, because we are able to find atoms that are stable. This only explains unstable atoms. Whenever the electrons are always revolving around it, it is explaining that those atoms are unstable, and as a result, to get to a point where those electrons should spiral into the nucleus. But it's not like that for real. So that tells us that it's a limitation to what Rutherford sees as the model of an atom. So this is a limitation, so let's tick it. Now, the second statement says It is applicable when energy is radiated in continuous mode. This is because it's unable to explain what we know as discrete spectral lines. Okay, so because Rutherford's model could not explain discrete spectral lines, that is why it is only applicable when energy is radiated in continuous mode. You cannot stop it at different spectral lines, energy at different spectral lines. This one tells you just continuously emitting energy. So that means this is also a limitation. Now, the third statement here says it is applicable to atoms with only one electron in the outer shell. Now, this is a limitation to atomic model, but it's just not the Rutherford's model. This is actually a limitation to the Bohr's model. Bohr's atomic model. Okay. Now, it's important to mention that these two are not the only limitations to Rutherford's model. In fact, there are about 5 limitations to the model. We've seen 2 already here. Another limitation is that it cannot explain chemical reactions between atoms. It cannot also not explain energy quantization. And then the 5th one being that it cannot explain the pattern for which electrons are arranged. It's just telling you that electrons are around it. It does not tell you how they are arranged around the nucleus. It does not give you a pattern for that. So those are the 5 limitations to the Rutherford's model. But for this question, we are able to see 2 of those limitations, which are in statement 1 and 2. And since the question says that we should identify the ones that are limitations, it means it is 1 and 2 only. And the options that says 1 and 2 only is option C. So the answer here is C. Folks, if you're still not subscribed to the channel, please kindly take a second of your time to quickly click the subscription button. It is important to us that you are subscribed to the channel. This encourages us to continue to make more helpful content like this. So please subscribe to the channel. And don't forget to always like and share the video so that you can help us reach our goal of reaching many students who are in need of helpful videos that we make. And if you have any question at all, please drop it in the comment section. Any question or suggestion at all, please put them in the comment section and we promise to attend to all of your comments. Just keep them coming. Now, this question says the photocell works on the principle of, now the photocell works on the principle known as the photoelectric effect. Okay. Now, what this states is that whenever a light source, or a light rather, of sufficient frequency or energy is incident on a photosensitive material. Now, photo there means light. That is a light-sensitive material. It causes electrons to be emitted from that surface. Now, this leads to electricity being generated from light energy. So you see there, what this is based on is the emission of electrons by the radiation of sufficient frequency of light energy or sufficient energy from light itself. So the correct option here is therefore B, which says emission of electrons by incident radiation. The process by which protons are converted into helium atoms with a tremendous release of energy is called. Now, we already know that we are looking at a nuclear reaction here. Now, there are 3 types of nuclear reactions. We have the nuclear fusion, we have the nuclear fission, then we have radioactive decay. Now, radioactive decay is where the nucleus emits particles spontaneously like that, so that it can then become smaller elements. Okay, so like when uranium, for example, emits alpha particle or gamma particles, as the case may be, to give you a smaller atom. Okay, but when we talk about nuclear fusion and nuclear fission, there's a clear difference between them. In the case of fusion, you are seeing light particles combining under tremendous energy to become heavier. That is, light nuclei come together to become a heavy nucleus. Okay, and in the case of nuclear fission, you see a heavy nucleus now splitting itself with the release of high energy to become smaller nuclei. So take note, fission, heavy nucleus becomes smaller nuclei. Why? Fusion, smaller nuclei come together to form a heavier nucleus. Now in this case here, we are seeing protons which are very light, and they have to come together to give you a heavier one, which is helium. Because helium is heavier, you need more protons to come together to give you helium. So when you have protons fusing to give you helium under tremendous release of energy, you are looking at nuclear fusion, and it is called thermionic fusion in this case. So the answer is therefore option C. The energy of a photon having a wavelength of 10 to the power of negative 10 meters is, so to solve this question, we're going to use the Einstein equation here, where we have E equals hf, which is actually hc over lambda. So we're using these two parts, so where we have energy. So the energy therefore is Planck's constant, that's 6.63 times 10 raised to the power negative 34. Then we multiply that by the speed of light, 3.0 times 10 raised to the power 8. Now, all divided by wavelength, which is 10 raised to the power minus 10. Okay? So when we multiply this, what do we have? That will give us 19.98. And it will be times 10 to the power of, this is minus 34 plus 8. When this comes, it becomes plus 10. So we have 19.98 times 10 to the power of, now this is 18 minus 34. So 18 minus 34. Let's do it the other way around. Remember, we'll have a negative answer this time. So this is 2, this is 14. 14 minus 8 will give us 6, and this will give us 1. So minus 16 here. And when we move this way, we can then say 1.998 times 10 raised to the power minus 15, and it's in joules. So the closest answer we have here is the 2.0 times 10 raised to the power minus 15 joules, because this is approximately it. So we then pick our answer as option A. In a thermonuclear reaction, the total initial mass is 5.02 times 10 raised to the power minus 27 kilograms, and the total final mass is 5.01 times 10 raised to the power minus 27 kilograms. Now the energy released in the process is, so given that the speed of light is 3.0 times 10 raised to the power 8 meter per second, we can then apply the Einstein's equation. That is delta E equals delta M C squared. So delta M, that is change in energy in the mass, that will be 5.02 times 10 raised to the power minus 27 minus 5.01 times 10 raised to the power minus 27. All of this multiplied by 3.0 times 10 raised to the power 8 all squared. So what does this leave us? This will give us 0.01 times 10 raised to the power minus 27 multiplied by 3.0 times 10 raised to the power 8, then squared. Now let's tidy all of this up. Now this can be written as 1.0 now times 10 raised to the power. Now remember, this moved 1, 2, so minus 2 here, that becomes minus 29. Okay, times, now 3 squared is 9, so 9.0 times 10 raised to the power 8 times 2, that gives us 16. So what we have here is 1 times 9, that is 9, so 9.0 times 10 to the power of minus 29 plus 16. Okay, so that is our energy there is therefore 9.0 times 10 to the power of, now the difference here is minus 13, and energy is measured in joules. So we have 9.0 times 10 raised to the power minus 13 joules, which is option A. If the threshold frequency of tungsten is 1.3 times 10 raised to the power 15 hertz, what is the work function? Now to find work function, when you have threshold frequency, remember that work function equals Planck's constant multiplied by threshold frequency. So Planck's constant is given as 6.6 here. So times 10 raised to the power minus 34. And then we multiply this by the frequency here. The threshold frequency is 1.3 times 10 raised to the power 15. So 6.6 times 1.3 will give us 8.58. Okay, so this will be multiplied by 10 to the power of negative 34 plus 15. Okay, and when you work with this will give you minus 19. So what we have is 8.58 times 10 raised to the power minus 19, and this is in joules. So the correct option is therefore A. Now, you can practice with questions like this and even many more by using the Exam Fund app. And what's more to it is that it makes your practice a lot more exciting. You get to solve questions at different levels where you earn points and even earn some money. So please click the link in the description box of this video to download the Exam Fund app today. And if you have any question or comments, please put them in the comment section and we promise to attend to all of your questions. And please do not forget to be subscribed to the channel. If you have not yet done that, you can subscribe by hitting the subscribe button, and you can also click the notification bell icon so that you get alerted every time we put out a new video. Now, I want to say a big thank you to those of you who have been following the series so far. This brings us to the end of day 38. The series still has 2 more videos to come. That is the video for day 39 and day 40. So I trust that you will be tuning in for those videos as well. So thank you for following the series so far. I'll be seeing you in the next video.